while on the grind, knowing that they're all quest to find. God gave us a gift, it's all by His design. You know what motherfucking time it is. Baby, it's hacking time. Hacking time. Baby, I don't wanna have no kids. No symptoms of family skills. Coming up on kitty scripts. I'm in production and pushing shit. You know what motherfucking time it is. Baby, it's hacking time. Baby, it's hacking time.
Dojo Dark Mage in the house with the sick flow. Listening to Evil Dojo Dark Mage in the house with the sick flow. listening to Evil Dojo. Dark Mage in the house with the sick flow.
What up, everybody? It's your boy, Dark Mage in the house with the sick flow. You already know. It's all about that code. What it do, though? I had an idea, and every so often, I'm just like fucking around with code, right? I take a lot of personal time to do research, to play around, to fuck around and find out, right? As I feel everybody should. Everybody, including non-programmers. Because how can you know that you're not a programmer unless you've tried to program, right? How can you know that you're not a math person if you haven't tried to do some math, right? Because a lot of times people kind of psych themselves out and think that they're not like good enough to even try doing something, so they just never try it. And then they try to like rationalize it backwards, suggesting that, oh, I know what's going to happen when I try to do this thing, so I'm not even going to try to do it. And people be like that sometimes, it's like fucking sad. Because, the world could be so much further along, for instance, if there weren't a lot of shitty math teachers, right? Let's take that as an example, because I know a lot of people hate math, and there are a lot of people who fucking suck at it, because either that's the nature of the distribution, which I don't believe to be the case, or my theory is that the education system sucks worldwide, and we are lucky when we can find a teacher who actually knows their shit. Or rather, it doesn't even have to know their shit. They just have to be passionate about improving their own shit and then improving others, right? Because and the way I think of it is, if I can teach it to myself, then I can teach it to one other person. And if I can do that much, then I can teach it to more people, so on, right? And once you've done something enough, you can start talking about it. And when you can talk about it with someone else, that's effectively teaching. So over time, teachers get better at how to do that talking and how to scale it up to reach like a wider audience, right? And that's one thing I've been trying to work on, because I am in a position where soon I'm going to have to start taking individual students again. And I want to get back into the habit of just like taking enough time throughout the day to actually exhaust my vocal energy in a way that allows me to get back into that flow. And perhaps before I even reach that point, we can find a way to make this work for me, because I'm interested in working for y'all. So normally what students do with me is they approach me with a topic or some sort of assignment that they're working on, or like a language, like they're in a class like CS 101 or CS 201 or fucking, some other class further down the line, programming languages, fucking software engineering, security class, whatever. And they'll be like, okay, we got this assignment and I don't know what to do. So they come to me and they're like, I will just not read the assignment and go to a tutor and ask them to do it for me. And I'm like, no, that's not how I work. No, we're going to do this together. Because if you're coming to me and you're going to expect me to take my time and you're not going to learn, no, you're going to be forced to learn. And I'm going to walk through with you step by step. And every opportunity where you can actually do something yourself, you're going to be doing it. Sometimes that even means me telling them exactly what to type. But the important part is that they're the ones to type it. Because even if you don't know why you need to type a certain line of code, going through the physical actions, I feel like, because you're going to go through the physical actions anyway, right? Whether or not you understand what you're doing. But getting that physical motion down to begin with, I feel like somehow is really important to the process, even though it's like completely tangent to the problem solving aspects. Sometimes people understand that better, but then they don't know how to translate that into the syntax. So that's where I come in. I've been doing this for a long time and I like it. I wouldn't be doing it otherwise. I like learning new shit. I like fucking around with old shit. I like going over the basics. Because there's a lot of people who don't do this and they forget. And there's also a lot of people who are new and who have never done it before to begin with. And today's material isn't really new to me or to anyone else. And it might be. And together we're going to try and do something new to me. And if it's new to me, then it might be new to a lot of you. And not a lot of people may be trying to do this. Or perhaps this is a different angle to approach a topic or multiple topics than other people might be doing. What do I mean by this? I know some YouTubers recently have covered material like, actually I saw one by Low Level Learning earlier today, actually within the last 2 hours, on malicious Go packages and Go packages getting backdoored. And it's like, whoa. And within the last few weeks, I've seen an article on malicious Python packages or things that, like, why Python's a bad vector, right? For security problems, or, you know, like a target for potential bad people, right? So while we're not bad ourselves, we are interested in the actions that bad people take in an effort to understand how we can kind of try and prevent them. Also understand, like, to what extent damage can be done, because it's one thing to say it, right? Like it's one thing to type it, right? Like, the experience of typing the code is different than the experience of the problem-solving thought processes that generate the lines to begin with. Because it's one thing for one person to tell you exactly what to type. It's another for you, the human being, to arrive at that typing yourself, to understand exactly why you need to type the things you need to type, and what the relationship to the meaning of the line is to the problem it is that you're trying to solve. Now, it sounds crazy from what angle, but this is also just a really top-down perspective on being a programmer and the experience of writing individual lines of code, kind of from like a really general problem-solving perspective, because every problem's different. The things that you might need to write in one program don't necessarily translate, but the basics are universal. And if you get the basics down, you can write anything. That's how I think about it. In the beginning, I didn't know exactly what to write because I wasn't focusing on making a game. I was just kind of like going with my interests, just going with curiosity's sake. And what that led me to was building websites in pure HTML as a kid, making text-based games in QBasic, and doing a bunch of UIL stuff here in Texas in Java for high school. But then a bunch of C stuff for college, right? Like homework problems and shit. I didn't do a lot of recreational programming back then. As a professional now, I do. And this is one of the recreational programs that I'm working with. So here's what we're doing today. We've got 2 programs. This is a small script, less than 100 lines, I've written, that allows me to encrypt and decrypt a file, a text file. Allows me to encrypt and decrypt a text file given a particular generated key Yeah, we have named key.key. This is generated from Fernet, which is imported from cryptography.fernet. And essentially what it is a base 64 encoded set of like random bytes. I think it's like 32. How big is the generated key? It actually doesn't tell us here. I'm not sure what the default. Let's see what the default is, right? So from cryptography import, was it Fernet? Let's see. One thing you can do in Python is, wait. Fernet.generate key. Yes. Oh, cryptography.fernet import fernet. Okay. Return to bytes of it. Oh, there. Oh, it doesn't really give us a whole lot of information. Well, the default is invalid input. What? I'm pretty sure this is base 64. Does it need that extra? Well, it's like 1, 2, 3, 4, 5, 6. It looks like 6 bytes, but I know it's more than that. We take this string, we add the extra equals in. Will this actually fix the padding? No. Okay. I won't mess with that anymore. But the point being, Fernet generates this key file, which we can use for symmetric encryption, right? So in symmetric encryption, you have a single key that can be used to encrypt or decrypt. With public key pair encryption, decryption, we have a public and a private key. So I have a generate key script here. It generates a public and a private key. Very straightforward. Now, using the public key, right, we can encrypt things. So the whole idea is, like back in the day especially, you'd see a lot of people in the dev world put up their public key so that if you wanted to send me a private encrypted email message, you take my public key, take your message, encrypt it, send it to me, and I'm the only one that they can decrypt it because I'm the only one with the private key. Because that sits on my machine, and I give everyone my public key and say, okay, you want to sign any messages so that I can read them? Or only I can read them. That's what you do. That's why it's a public key. It's a key you can give to everybody. And depending on the context, depends on who gets what, right? Like, if I wanted to be the one who was doing the signing, right? Like to prove that I am the one who owns the message, like I am the one who did it, then I would sign it with my public key. And on the but in that situation, it would have to be a different like key, right? Because if you're giving everyone the public key, they would be the ones who are able to sign it. So naturally, that makes sense. Because there is a difference between using this technology to create a secure encrypted message that, can, only be read by one party, and using the technology to create a digital token that uniquely identifies yourself, right? You could, there's a little bit more exploration definitely in that department, but here's what we're going to do today. So this is the beginning of a encryption script that I'm writing. We're going to finish it up. That uses the public key to encrypt a message, and we'll also write a decryption script. But what we want to do with this in conjunction with the symmetric, with the AES script, is put them together. Because imagine, if you will, you want to encrypt a file, and here's how you want to encrypt it, right? Like, because one of the problems with the previous script, with the AES one, is that the key sits on the file system at the moment, right? That's bad. We don't want to give people the key, right? Because then they'd be able to decrypt their files, and we don't want them to be able to do that, right? So here's what we're gonna do. Like, let me just finish up what I'm doing. I'm always bad about talking and coding at the same time. Come on, Copilot. Message equals hello world. Yeah, sure. We'll use that as a demo message. That's fine. Crypto.txt. Um, before we do that, yeah, we want to base 64 encode it. No, we just want to. Yeah, sure, why not? That's true. It did like do print like fucking Python 2 style there. What the hell? What the hell? That's a bug in the encryption module. Hmm. That's interesting. What's going on here? All right. This was the original default. Okay, it still doesn't like that. Let's try doing it from the command line. Import RSA. How's everyone doing today? Yeah, it's got RSA encrypt. Must be a string no longer than k minus 11 bytes, right? Yes. Oh, and it has to be a byte message. It has to be a byte string. Oh, yeah, yeah, yeah. Okay, okay. So 1, 2, 3, 4, 5, 6. So remember, we just generated a new key, right? So the maximum message length is 53. So in this case, we can just say hello world. Um, really? Still? Or is it 53 bits or 53? I thought it was bytes. Okay, it still doesn't like that. Oh, but the program was yelling about okay, so here's what they're doing here. They're actually creating a new key like right here. And I think what's happening is the reading is failing here. Um it's not correctly loading in. Yeah, I just got that. Thank you. No, we're totally in sync. So, uh, gotta be like a load key function or something, right? Yeah. Here we are. No, but that's for dir. We want the load pem right here. Now, what are the parameters to that again? Um, oh, so we can actually just call load the. We can actually just call this. Um, and we pass it the file name. Whoops. I meant RSA dot, but even that's probably not correct. Um, private key. Wait. Where was that at? Oh yeah. Okay, so we have to declare a new public key and then call this. Wait, like that? Yeah. RSA Public Key. N and E, what? Um, five and three. Load public key. It's a class method, so I should be able to just do that. Uh-oh. Oh, we have to specify the format. But it defaults to PEM, so I mean, there's our public key. Load PKCS1. Okay, so we could actually call the full function. Yes, I understand what the order of operations is. We have to finish getting this half working first because we already have the AES part working first. Interesting to add the additional hashing step in between the two. I like that. Is that necessary? And why SHA-2 instead of another one of the SHAs? Because this is actually an interesting thing to think about. Because I honestly don't know what the optimal parameters are, not to mention there's other hashing functions besides SHA. But typically, you know, most people go with industry standard and whatnot. But there are new things emerging in the space. There are quantum resistant functions being developed, and OpenSSL-PEM. Oh, I guess it didn't get written as bytes when we generated it. I think that would be the problem. Now we're going to gen keys again. Uh-oh. Wait, what? Oh. Um. The hash verifies the integrity of the message, and the signing provides authentication that is the correct hash. Okay, so it's just like a pre-hashing step, and then you sign the hash. Okay, no, that makes sense. I get that. That's a good explanation. Thank you. You should be able to load a PM file into a keys object to use with the signing method. One second. Okay, we have a new public that has been written. Is that right? Oh, we gotta do this one also. Make sure to write it as a bytes file for when you load it. You could do this a number of different ways. This is just how I'm doing it. All right, we have our new wait. Okay, I mean, there's that, and then you need a private key PM file. Yeah, we've got a public and a private. Oh, begin RSA public key. They're looking for just the words public key. Interesting. Okay, no. No, we're getting closer to the problem here. You see this? This is saying it's looking for begin public key, but what's actually being written is begin RSA public key. So, what's up with our gen keys? Why is the header different? Is it so easy that I could like actually delete them and it would still work? I don't think that's right. Maybe, I mean, if there was like a P, because this is expecting OpenSSL formatted. No, it doesn't. It actually wants the file name. We just verified that in the help. Like if we go back to import RSA, help for public key, then you go down to load. Oh no, wait, you're right. Sorry. This actually it does expect the contents. Okay, okay. No, that's not the problem. Wait. No, it's still not the problem. Um, oops. See, look. Here's what's being written for the key file generated. But the reading method that I'm using expects OpenSSL formatted key structure. So this reads it as an RSA, right? But I forget exactly what the command is in OpenSSL. You notice that they have different methods here. They have gen RSA and gen pkey, and I wouldn't be surprised if the right, exactly. That's exactly what it is. So the question now is, do we fix the loading to handle RSA, or do we fix the key generation to load to generate OpenSSL? Or better yet, wait, no valid start. What? Begin RSA. Okay, now this one is actually writing the correct. Like now we're matching correctly, but something's not quite right here. Because this is the start marker, and we do have the start marker here now. So now I think we actually do have to load the contents. Uh-oh. Wait, no, it has to be read in as... Wait. Oh, yeah. We have to change this to pub. All right, here we go. Okay, we got it. Okay. Actually, thank you. You have been a valuable pair programmer in this stream so far. I do appreciate it. So now we've got that worked out. Now we can go through the process of doing a test encrypt on a small message. Because from here, of course, we're going to go through that process next. Now, here's the thing with your whole idea about hashing the contents in the middle is that if we do something like this, then we need to be working with like hash only objects and whatever storage mechanism it is that we're using on the back end of our command control, system that we're creating here. But this is also like we're doing it at this level for a couple reasons. One is that we want the flexibility of being able to apply the system to multiple different use cases. One use case is going to be in the context of encrypting local files in a way that the key is going to be irrecoverable to the user, or rather the person running the program, but instead the key will be shipped off to another location because it's going to be generated on the fly on the system at the time of program run, so that when the program's downloaded or analyzed, you can't actually know what the key was, because we're going to end up generating that RSA on the fly and then encrypting it using our public key, and then base 64 encoding that and then shipping that off to another location. So by doing this, what we're going to be able to do is hand the key off to some master who is, orchestrating this mass evil plot where they're, crypto ransomwaring, tons of computers, and need a way to ethically provide a way to decrypt these files later on. Because ultimately, for that person's job, the ultimate, end game is key management. But if you hash the keys before shipping them off, then they're irrecoverable, because the hash is only a one-way function, right? You can't like reverse the hash once you've hashed it. If you were like doing like password-based authentication, this would make sense, and you would want to do something like that. So that's another context where the additional step would be very desirable, because then you could actually like encrypt your hashes in your database, and so that you have like a further layer of authentication in case some evil hacker decides to break your database and download all your shit. What a lot of companies have done in the past, which has been bad, is like storing contents in plain text, or like not salting their hashes, or doing something other, that makes it easier for them to decrypt and get the contents of each individual user's account passwords. We're not doing that exactly, but we are exploring the beginnings of this. So afterwards, we want to encrypt. So far, so good. And let's start by just printing crypto. Uh-oh. Okay, so crypto is bytes. So we need to... There we go. Okay. So now we have our first RSA encrypted message using public key. And the whole idea here is the public key we're going to want to include in the script because the end goal is that when, the unsuspecting user runs the program, they, the AES key is generated on the fly and kept in memory, right? And we do all of our, local file encryption using that key. But then we also sign our AES key using our public key in RSA. Now it's encrypted using our public key, and it can't be decrypted without a private key. And at that point, because instead of message, this will be AES contents, right? This is going to be an AES contents of bytes that are read in from somewhere else. And we take that, and that's what we actually ship off to another location. So the end goal here is a RSA signed AES generated key, right? And we want to be able to do this on the fly. So every time we run the program, we get a different key, right? And we're not going to do a whole lot in the actual scaling up of this today, but this is kind of like part one of a series on what could go wrong with such program, right? So we got our public key. So this is step one, right? Step two, let's take a look at our other program. Now, we're doing it this way. So this is like a little optimization technique. This is something that you can do in multiple programming languages. So as an example of this, we're going to go ahead and cat public key. Into the encrypt script itself. So this is one way we can do it. There are public key stored directly in the source code itself. We'll call that pubkey, and we're going to call that pub. Now we no longer need to actually read the key file, right? Because it's directly in the source. Now notice every time it's given us a completely different message, which I find very interesting. What was the flag for hex dump? It's yeah, canonical. All right, so this is the very beginning, right? So now we said earlier we were going to replace message, right, with our actual AES generated key. So we're getting a completely different key every time we do this. So with the original key file, and actually is it actually writing it out as a okay, it's actually generating a byte string in base 64. So as you can see, they're the same contents. As you can see, when it prints out just a ton of bytes. how many bytes is that versus how many bytes are returned by the AES key string, right? Invalid base 64 encoded string. Oh yeah, yeah, yeah. Um Wait, what? There we go. Okay. Base 64 encoded string. Oh yeah, yeah, yeah. Yeah, so it's naturally less characters, right? And it's only 32 bytes. So all you would have to do to convert it between formats is to base 64 encode the bytes and then base 64 decode the key like this. So all we have to do now is as you can see, it's a byte string. End up with a slightly shorter message by doing base 64 decoded key string here. Incorrect padding. Uh-oh. Oh, it's probably too long. Fuck. Really? Mm, okay, once bytes. Incorrect padding. Hmm. Okay, so the key length is still within shot of our message length. But the whole idea here is that now one of the things that we would want to think about in being able to transmit this message to another location. I say this message, specifically this, because if we encrypt a AES key locally, like we're doing here. So like we have a public key and we have a on the fly generated AES key. And we want to transmit this key to another location in a way where, you know, the amount of time it's in memory is rather minimal, and we can actually I'll put some more truth to that statement. This forces them out of memory. So we generate AES key on the fly. We encrypt it with our public key. And then we have a base 64 encoded RSA encrypted AES key that we can transmit somewhere. But I feel like we could do better with the with the transmission, right? This base 64 is okay. Like we can post it somewhere. We can probably put it in a GET request. So for instance, you could like have a Flask server running somewhere or multiple Flask servers that like just wait for GET requests from like infected machines. And you transmit this base 64 encoded string in a GET request like you take this whole thing and then you could have something where you go like get slash storage slash ID slash and then this. But then you have the problem with the slashes. So you might end up like posting it instead. But you'd post it to like a Flask server that Flash server attempts to use its private key to decrypt this, right? Actually, now would be a good time to do a decrypt. So our goal here is key recovery, right? Because the server is going to store the decrypted contents, assuming that the decryption is good. If the decryption fails, it is perhaps like a malicious actor trying to sabotage our efforts by posting invalid sign data, right? So it's up to us to do like data integrity verification in order to make sure that whatever it is that gets posted is actually good. So we've got a private key, right? Just like before, we're going to have the private key directly in the contents of the file. So we're basically going to use this as input to the next program. So whenever we run this, we can pipe it or copy paste it directly into the decrypt program to recover the key. The whole idea is that this is kind of like the workflow that we would expect to occur in a situation where someone ends up getting ransomwared. You run a malicious program, it creates some encryption keys, it encrypts some stuff, it ships off the encryption key to a server for storage so that it doesn't get lost, and that way no one in between is able to actually see what that key actually is, and then stuff happens. So So based on the way that we did the encryption over here, we decode and then encode, or rather we encode first. Let's see if this works. All right, so that should be our key. So if we want to verify this, here's the generated key, right? We take this and then we paste it in here. And as we can see, this is the exact same string as up here. So this code works. We have slapped together something that's functional here. So if we were to pipe this all together, so we can take the outputs of this and pass it directly into our decrypt program. And this is what our server would be able to see whenever it gets a receipt from a new machine saying, hey, we got one. What's up? Here's the key. And then, presuming that, you do the rest of your homework correctly, you would create the infrastructure necessary in order to present a message to the user, letting them know, I'm very sorry, but your machine has been ransomwared. If you would like the decryption key, reach out to me at and give us your money. And upon receipt of the money, and you could actually set up a totally automated system that ships the keys off to people in the event of receipt of payment. You can set up like webhooks and triggers so that, upon receipt of a certain amount of Bitcoin, a certain function runs that, for instance, given the appropriate contact information, provides the decryption key as well as the program necessary to perform the decryption. And it gives instructions on how to do that. So there would have to be some sort of uniformity, or, like if you're handling multiple operating systems, you have to be able to handle for all of these different edge cases in order to do so in a way where, you're not like totally fucking people over, because it is fucking people over already. But if you want to be at least like business-like about it, like, come through with your fucking promise and actually deliver on a service, and a service being both the encryption and decryption of files, that's exactly what would happen there. So, someone would receive this on their back end, or at least they'd be able to see it because they have the private key. And unless they get compromised, then there's no problem there. But let's talk about nightmare scenarios before I go, because in the future we're going to come back and start building out examples of like encrypting a local file using the source structure, and then also properly receiving the key, so that if God forbid this happened to someone, that they can actually reach out to the operator and say, please, I've got your money, please decrypt my shit. And they say, okay, we got you. We have received payment of your funds, and we will go through that process. I'm not encouraging anyone to do this. I'm not saying that this is something that should happen, or that is like a thing that should be out in the world or anything like that. I totally abhor the practice itself. But it's really interesting to walk through the steps and to understand the mindset and the operation tactics, and even the basics like we're doing right now. Understanding what exactly happens at a fundamental level when one of these events occurs at a big company where they end up getting ransomwared and hundreds, if not thousands, of machines end up locked up, and nobody's able to access their shit. And this includes critical system files. And this could happen for any number of different reasons. And this is one reason that it could happen, is that someone accidentally runs some code that they shouldn't run. Something like this could happen because of the result of installing and running a malicious Python package that's been uploaded to pip. This has happened more than once. Python package squatting is a big deal, just as big a deal as like typo squatting on domain names. So there's a lot of different things that can go wrong, and I wanted to begin exploring the underneath the hood of all this, and understanding different ways that machines can communicate with each other in a way that is effectively decentralized and allows for a flexibility of control where, for instance, let's say, we talk about nightmare scenarios. What if the ransomware operator loses the private key for some reason, right? For any number of organizations, because one thing you could do is distribute, like, let's say you've got 25 organizations that you've ransomwared. You could have 5 of those organizations assigned to a particular private key, and then repeat this process for others in a way where, like, if you accidentally lose access to one of the keys, not every organization is totally fucked. But the reality of that situation is, if you do lose your private key, you are fucked. And you better hope to God that if you get ransomware, that the ransomware operator is competent and doesn't lose the private key. In the worst case, a ransomware operator is not operating in good faith, because they're already not operating in good faith, right? But they're operating in even more not good faith by, like, think of that girl from Saw 2, right? The protege. The protege was really into the idea of unwinnable games. And this is, I think, a true fundamental distinction between, like, real evil and, like, not evil. Like less evil. It's still evil, but, like, is a less form of evil. Like, we're talking about, like, real pure fucking malice. That's the kind of shit we're talking about there. So let's operate under the assumption that we hope to God that individuals in the space who happen to be so hard up for cash that they have to go through this process, that they're not just being greedy, and that they actually have things they have to pay for and deal with. Families, etc. Because everyone's got to find a way. And if, these are your only means, I'm very sorry for you, but I also hope that you're not so bad of a person as to not give people a way out, or to not deliver on your promises, or to, you know, make something so inescapable that it's life ruining. Because a company can easily afford, you know, a certain amount of money in order to get their stuff decrypted. And it would also offer them an opportunity to figure out the vector of entry so that they can try to patch that and fit, you know, prevent it from in the future. At the end of the day, I think the overall lesson is don't run code that you don't trust. Make a very strong effort to avoid running code if all possible, because then the trust issue isn't even a question. But if you have to run something, make absolutely sure. If you install something, make absolutely sure. So we've learned a little bit about encryption and decryption in RSA and AES. If you enjoy this kind of content, you enjoy me talking about hacking, figuring shit out, teaching stuff, hopefully everyone learned something with me here today. Shoutouts to Big John on YouTube for playing Pair Programmer today. It was a big help. Interesting discussion. I had fun. I hope y'all did too. 90-minute class. That's appropriate. That's what I feel about the vibe. You know, I can do this for about an hour and a half, 2 hours before I burn out and I need to fucking feed myself. Dogs are freaking out right now too, so maybe it's a good time for me to go.